But we're going to, just so you'll know, we're going to be creating shapes and determining the volumes of those shapes. That's our goal with what we're doing today. And we're going to start off kind of where we were and then going backwards and coming back to it and trying to tie it all together. So let's look at this problem that I've got in front of you here on the first page of the notes. Find the area between the given curve, y equals x squared, the x-axis, that's this line down here, and the line x equals 1. That's that line right there. So we're looking to find this area right here. And I think it's important for you to get accustomed to writing it down and drawing the picture and doing a little bit of shading with these, because as we start twisting and turning these things, it becomes more challenging. So how do we do this? We're going to integrate. Is it dx or dy? Dx. Okay. What are our limits of integration? 0 to 1. And what are we integrating? X squared. Now, we normally have a bottom to it, but in this case, we don't have to because the bottom is just 0. So we're integrating x squared, and we get x cubed over 3, evaluated at 0 and 1, which comes out to be a 1/3. So that's the area there. Now, I want you to go back, though. How did we find area? When we started in January on this, how did we go about estimating finding these areas? Lots of little bitty rectangles. We would come here and we said, okay, if we go at this point and we make a rectangle up to here and over to there, we can find the area of that rectangle and the area of this rectangle and this rectangle and blah, 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 blah. And if we add the rectangles together, we get an estimate of it, right? And if we make the rectangles slimmer, instead of 2/10, if we made them 1/10 each, that puts more rectangles. That makes the estimation more accurate. And just the more rectangles we get, the better off we can get there. Well, now I want you to picture in your mind what happens when we take this curve and we're going to rotate it around the x-axis, around this green line here, okay? And that's what this little application here does. See, there is that right there is what our curve looked like. That's y equals x squared. And if we rotate it around the x-axis, and now we're going to come and look at it from down here, okay? We're going to look at it from down here. That's what we get. We get a funnel-looking thing, okay? So now, the question that I have for you is, how do we figure out what the volume of that funnel is? How can we figure out what the volume is? No, you can't build one and pour it full of water and say that's how much volume it is.
Guessing, we're going to find out.
You are correct. We're going to have to figure out. So I want you to take a second. You got an idea for me, Sir Beth? Well, what's the worst thing that happens?
Well, we want to find the volume of a square, of a cube, when you have a square. Picture, I actually had something for this.
Square is length times width. So the cube.
Is length times width times height.
So you got to multiply it by something else.
So yeah, you add a new factor that shows the fact that it has a new dimension to it.
Okay, so everybody hear what he's saying? He's saying if you've got the area, if we need another dimension to multiply that by. Okay, there's some logic in that, I think. There's some logic in that. Now, so anybody got any other ideas they want to throw at us here?
Circumference?
Yeah.
Circumference, okay.
That was not the circumference, but the flat area, surface area top, because we already have the surface area in the little.
All right, the surface area of the top. Now, talk to me about that. I'm not.
Like when you put the bottom for those facing you.
Gotcha.
That circle right there.
Right here. You mean this circle out front here?
Yeah.
Yeah, finding that area. Okay.
And then using the other part of the area that we found a minute ago for the sweet thingy
Mm-hmm.
together.
All right, now let's think about this for a second. Does everybody understand what she's saying? We found a while ago that the area was 1/3. And she's saying if we find the area of this circle here, and what you want to do with those two things? All right. She says, I think we'd multiply them. So let's go here for a second. Let's chase this for a second. With the area that we just found over here, what would the units be? Square units, right? And if we find the area of this, we're going to get square units. And square units times square units gives us fourth units, and that's the fourth dimension, and we aren't going there, okay? But that's a good idea. I want you to take this. Let's go back. Yes, ma'am. Got another idea?
You have it like that, and then you just like, then if that makes sense, that's the area from the top. Like, that area 1/3 is like the flat part of it. So you just need a bunch of them to make the whole circle. I just don't know
Excellent,
what
excellent.
ones you need.
Does everybody understand what she's saying? She's saying we know this area is 1/3, and every time we turn it, the area is still going to be 1/3. It's just going to be slightly over. So if we could add all those together somehow, we could get it.
This is what I'm getting at.
Yep.
Big circle.
Excellent deductiveness there, okay? Excellent. I want us to go back to where we were here, making these rectangles. What if I take this little bitty rectangle right here? All right, now I'm just going to take this red rectangle here, and I'm going to sweep this red rectangle out of the board, around the green line, and back all the way around. So I've made one complete revolution there. What shape do I have? A circle, but it's got a third dimension to it here, doesn't it? So it's not really a circle if it's three dimensional. What do we call it if it's three? It's a sphere. It's a cylinder, actually. A sphere is rounded. It's a cylinder, right? Okay. Now, how do we find the area of a cylinder? Does anybody remember?
You take the circumference and multiply it by the. I knew this. Right.
That's surface area.
It's going to be like 2 pi r squared times the height, right?
It's pi r squared times the height.
Yeah.
It's pi r squared times the height, okay? Now, I want you to keep thinking about this here, okay? If we sweep this out and around, when we sweep it around, we're going to have a circular front, if you will. I'm going to rotate this around here. We're going to have a circular front. That's what Sarah Beth was talking about here. So we're going to find the area of that, pi r squared, times the height. Well, the height is going to be this width right here. Y'all with me there? So to find, if we were to take this thing and sweep it out of the board, we would have pi r squared, which is going around it, times the height, and the height would be this distance right here. Okay? Y'all with me there so far? Now, what's the difficulty with finding how would you find pi r squared here?
The radius is how, because there's 2 different r's and 2 different points on an r.
And now we have a conundrum.
Wait, I got it.
Because, see, if we measure the radius here, we're going to get one value. If we measure the radius here, we're going to get another value. Would you agree? But where is the happy medium that's going to be the right one?
What if we were to, what we need to do is we need to do like we're integrating between 2 points, with our 2 points being our 2 radii. Radius, like tell my thumb with a larger radius, my smaller radius.
Very similar to that, yes. Very similar to what we're doing there. But now, if you think about this problem that I've just posed to you, this is the same problem we had right here with these rectangles, right? Because we know that if we go back to doing this the way we originally started and find the area of this rectangle, that's not going to be the actual area of this here, is it? No, and even if we go use the right Riemann sum, if we go over here and use that rectangle, that's not going to be it, is it?
The trapezoid thing.
The trapezoid would be closer, but it's still not going to be exact. How do we get exactness here?
We would have to integrate it from 0 to 1.
Right, but from a rectangle's perspective, how can we get more exact? More and more rectangles. So if we put more and more rectangles in here, every time we put more rectangles in, suddenly we're getting more exact. And when we put all of the rectangles in there, is when we're doing what we call integration. So that's where we're headed with this. Even to get this region right here, we are going to have to integrate it. The integration is going to take care of our width part here. We've just got to figure out the area in here. The pi r squared part. We've got to figure out how do we do the pi r squared. Okay, that's where we're headed with this, okay? Now, the difficulty, as y'all have just pointed out, is the radius is different here than here. But the radius is different everywhere on here, isn't it? What's the radius at any given point? Can anybody tell me? That's right. The radius at any given point is x squared. And why is it x squared?
That's the y value.
Because that's what our curve is. Our curve is y equals x squared. So the radius at any given point is this value up here. So what we've got to do then, in order to find the area of this thing, and let me take a picture of this so I can take all of my crib notes over there. Whoops, come back to here, here. If we take all of these things together, and if we want to find the volume of it, we need to integrate with respect to x, 0 to 1. That's from here to here. We need to, now remember the dx is this distance down here, correct? So our dx is kind of like our height. What did we say we needed in addition to the height to find the area of a cylinder? Pi r squared. Since pi is a constant number, I'm going to write it out here in front of the integration symbol. And what did you say that the radius was squared? What was the radius?
X squared.
The radius was our function itself. The radius was x squared. So in order to find the volume for this thing, it's pi 0, 1. The radius squared, which is x squared, squared dx. So we will be able to find the volume of that shape by integrating that. By integrating, because here's pi, radius is x squared, is pi r squared, dx is your h, dx is your height. Remember, we're taking care of the height by doing the integration part from 0 to 1.
So the area is pi.
So the area is going to be pi times x to the 5th over 5, evaluated at 0 and 1, which is going to be 1/5 pi. That's our volume. That's our volume for if we were to take that curve and rotate it around the x-axis.
That's not much more than 1/3 then.
Remember, it was 1/3. Now we've got 1/5 pi.
I know, I multiplied pi.
So you're right. It's not a whole lot more than 1/3. You are correct. The volume and the area don't always stay in the same relationship there. So, if in order to find the area, to find the volume of something revolving around the x-axis, what's our formula going to be? We're going to integrate with respect to x from one point to the other, and I'm going to denote this by capital R of x squared times pi. Pi r squared h. If you can think of it in that terms, pi, our radius is this capital R, which is how far it is from the x-axis to that curve, which should be the function itself, squared. H is the integration component of it. Integrating the dx gets us our H in there. Now, conceptually, that's where we're at, okay? Let's get down to working on this. What does it look like in real life? Well, this isn't real life. This is made-up life. This is math life. Determine the volume of the solid obtained by rotating the region bounded by blah and the x-axis about the x-axis. This is what our pictures would look like, okay? Here's our function in red. We're looking to rotate this green region around it, and this is kind of the shape that we're going to get when we end up with here, okay? I can go back over to, let's go over here and integrate this puppy. What are we looking at? It's x squared minus 4x plus 5?
Yes, sir.
Plus 5. And we're going from who to where? 1 to 4?
Oh, yes, sir.
1, 2, 4. And if we plot that, see that we've got something that looks like that there? And if we rotate that, that's what we get. So here's what we're looking at. Something like this. We're asked to find the volume of that. Are you with me? Okay, so what does our integration look like? We're integrating what? 1 to 4. X squared minus 4x plus 5 dx, almost. Couple of things missing here. What have we missed? Now, I'm not trying to find the area. I'm trying to find the volume. We've got to square it. Square it and pi, okay? You need to square it and pi. Here's another case, and I'm going to take a second and pull up my calculating device. This is another one of those things that I'm going to put into my calculator probably. Remember, I've got my y1 minus y2 and my y2 minus y1 in there. If I come down here and I want to put in the first thing squared. Is that it? Oops, that wasn't it. I can't read. Y variables, functions. Find that squared. So now when I go, I can go and put this function up here, x squared minus 4x plus 5. So there's what I'm looking to graph. That's the graph. I'm looking to integrate, though, this number 5 down here. So I'm going to, on my calculator, go second, calculate. I want to calculate the integration of, what did I do wrong? Oh, because it's not a y2, it can't graph it there. Now understand, this is just so I can calculate the integral. I'm gonna put it in there. I'm only going to graph the y1 squared, and I know that my graph is not going to look like what I've got over there, okay? I know my graph's not going to look like anything. The limit's from 1, lower limit's 1, upper limit's 4, and that's because my window's not right. Window. Zoom, standard, 6, boom. Now, see, that graph's not going to look anything like what I'm doing there because, remember, I'm not graphing this, I'm graphing that square. So we're going to calculate 7, the lower limit's 1, the upper limit's 4, and I get 15.6. That's my volume of that if I take it and rotate it around the x-axis.
What'd you get as the volume again?
I got 15.6.
That is not what I got.
Okay. What did you get?
I got 195.6.
Oh, I haven't multiplied it by pi yet. You're probably right then. If I do that times pi 49. I forgot to multiply it by. That should be the correct answer there, the 49.008.
I probably just.
Did you put in your function? Did you square it? Did you integrate it from 1 to 4? Did you multiply it by pi? By pi?
Let's see here. Squared it. I got x to the fourth minus 4x squared plus 25.
Is not what you get when you square this trinomial. You should get 9 terms out of that thing, son. You're going to get an x to the fourth, an x to the third, an x squared, an x, and a constant.
Okay,
Yeah.
I realized what I did wrong. I just
Yep.
added square.
Yep.
I squared everything into actually.
You do not want to do this by hand, people, okay? You want to use your calculator because squaring this thing out, you'd have to square this trinomial out before you could integrate it. It's going to be ugly. You want to do this with your calculating device. We expect you to do this with your calculating device.
And so it's pretty much the same. You just plug it in, do the integral, and then just after you get that done, just multiply.
Multiplied by pi. That's all there is to it.
Okay.
But you can make all types of interesting figures with something like this. And we're going to look at a couple more before we stop for the day here. The volume of the solid formed by revolving the region bounded by the graph of root sine x on the x-axis, 0 to pi, about the x-axis. So we're going to take this region right here, and we're going to rotate it around the x-axis. Okay? So when you get through rotating it, you're going to have something like this. You're going to have something shaped kind of like an egg. Okay? That complicated enough? All right. Well, so what's our integration going to look like? 0 to pi. Yep. It's going to be the square root of sine of x squared, which does come out just to be the sine of x times pi. Pi r squared. Pi r squared.
The integral of square root of sine of x.
Well, but the square root squared just gives you sine x. So you're going to be integrating from 0 to pi times pi of the sine of x dx. What's the integral of sine? So we've got negative cosine evaluated at 0 and pi. So that's what? Negative 1 minus 1. Cosine of 0 is 1, and I've got a minus sign in front of it, but I had a subtraction in front of all of it. I think we just get 2 pi for an answer. That's the volume of it. Does that seem complicated yet? And it's not going to get a whole lot more complicated today. Let's look at, see if we can find some intriguing ones. Where'd that come from? Okay. So let's look at this particular problem here. Set up and evaluate the integral. I don't care about evaluating as much as I do setting up the integral. What would be the setup for this? What would my integration look like? What would my... Sarah Beth, what would I be looking at? 0 to 1. All right. Is everybody comfortable with that? That's what we've got there to integrate. Now, that one's simple enough to where you could actually square it out and do it by hand if you wanted to. I'm not concerned about you doing it right now. I'm confident you can do that. Do y'all have this in your... There's the next one. Okay. That's something I should have done. Let's set up number 2 here then. y equals 4 minus x squared. And we're rotating it about the x-axis. So we're integrating. What are our limits of integration, Kevin? 4 and 2. Why 4 and 2?
Oh, wait, 2 and 0.
2 and 0. Why 2 and 0? Yes, we're going this way, so it's dx. Remember, and this is, I'm telling you this over and over because if we add to this tomorrow, Wednesday and Thursday, that's when it starts getting confusing. We're using the x numbers, x equals 0 and x equals 2, okay? We know we've got a pi because we're revolving, and what is our radius every time here?
4 minus x squared.
4 minus x squared. So that's my radius, 4 minus x squared, and we would work that out. You and your calculator would work that out, and you could get a relatively easy solution. So when you're doing problems tonight, I want to see this. Your answer is great to have too, but this is the main thing I want to see. The fact that you can copy the answer down off of CalcChat doesn't do me any good. The fact that you copied this off of CalcChat at least tells me you had to look at it and think about it for a few seconds, okay? So be sure that you get this written down with your homework, this that you're looking at right here. All right. Any complications with what I'm doing here? Is there anything I can do to make it more complicated right now? What would our limits of integration on number 3 be? 1 to 4, because that's what the shaded region is every time, okay? This is square root of x squared dx pi. Do you realize that this is the way some of the formulas that you use have been developed? Like a cone, for example. If you remember, the cone is 1/3 pi r squared h, I think. If you work that out with a line, that's exactly what you get. So many of the area and volume formulas that you use were developed by using these methods in calculus there, okay? Now, just something for you to think about. Take that thing right there and rotate it around the y-axis.
Isn't it the same thing? We just flip it, like instead of y equals square root of x, we just do it with x equals y squared.
Okay.
How we do it in our thing of integration is from 1 to 4.
That's right. It's going to be a totally different shape suddenly, isn't it?
And we do it, like, limits of integration will be from 1 to 2.
Why 1 and why 2?
It's moving 1 to 4, it starts at 1 and goes up to 2. Or wait, no, it starts at 0 and goes up to 2.
Mm-hmm. See, that's where we're headed to, is to get to something that's more challenging there. But for today, I don't want to give you anything more challenging than what we have right there, okay? So this gets you, there's a few problems, and there's very few problems that I've got listed for you for homework tonight. I think there's just 5 or 6 problems there. The most important thing is to get it set up correctly, okay? You've got 2 FRQs due Friday. Do y'all want to go ahead and begin working on your in-class FRQ now?